Hello to everybody once again. It's a pleasure to introduce Mr. Telemachos Panagiotakos. He's a bridge expert, also coming from Praxis, specialized in seismic devices. He's a CEO and head of the Bridge Design and Special Projects Departments of Denko Structural Engineering, worked also as postdoctoral research associate at the Department of Civil Engineering of University of Patras in Greece and at the University of Rome of La Sapienza in Italy. He has been involved in the structural design of all types of bridges, building complexes, as well as in the assessment and structural upgrading of existing structures. He was a lecturer at the Department of Architectural Engineering of University of Patras, involved in both research and drafting of Eurocode 8, Part 1, as well as Part 2, and in the Greek Code of Structural Inventions. He's a national representative to the Eurocode 8 Committee, Earthquake Resistance Design of Structures. Thank you very much for your today call. Please, the floor is yours.
Thank you very much for this kind introduction. I'll try to be short to gain a little bit of time and to have more time for questions. This presentation focuses on the design of bridges equipped with antiseismic devices. We cover only additional requirements that is already appears in the part 1 of the second generation of Eurocode 8. The clause cover the design for bridges with antiseismic devices in part 2 of Eurocode 8. It's a very short chapter. We have only, I think, 3 or 4 pages, and it's divided into 5 subclauses. General one, is very short, describing the seismic action, the basic requirements, and compliance criteria. And also the third subclause covers the general provision concerning antiseismic devices. The next subclause covers the methods of analysis, and here we have the already mentioned by Professor Franchin, the methods of analysis that is applicable for bridges, and we remind you that this is equivalent linear analysis with a lateral force, also degree of freedom system, with the response spectrum method, as well as the response history analysis. All these 3 methods is also applicable for the design of bridges equipped with antiseismic devices. And the last section covers that Mr. Davi already mentioned about the minimum overlap length at connection that is a requirement provided in this clause. Why we have to redraft a clause that is appear also in existing part 2 of Eurocode 8? Everything starts from the mandate, because the mandate, it's clear, requires that the section for the seismic isolation should be updated given the most recent technologies in the passive control, and improve the interface, and this is very important, between the design standards such as Eurocode and the product standard such as the EN 15129 for antiseismic devices, as well as for the product standard for structural bearing, which is 1339. So, based on the mandate, we have to redraft the section 7, now section 8 of the part 2 of Eurocode 8 to move, omit, or redraft special provisions. Also, we have to cover fully isolated, and this is an innovation, also partially isolated bridges, which is not appears in the current standard. And we have, as required by the mandate, to improve the interface between a product standard and the Eurocode. Also, I have to mention this. This is the reason why this clause is very short. All the common principles that is required for the design of bridges with antiseismic devices has been moved to part 1.1. which is the main part for design for the seismic design of structures in general. So in this presentation, I try to divide it into 5 parts. The first cover what is the antiseismic devices. And the rest 4th part cover specific provisions that we have in part 8 of the Eurocode. Start from the existing part 2 of Eurocode 8. In the existing part 2 that we use today, we have the terms seismic isolators and seismic link. This is the only terms that describe the seismic isolation as well as the seismic links that we use in the current practice. And its definition for the seismic isolation as the provision of bridge structure with special isolated devices for the purpose of reducing the seismic response of the bridge. And the seismic links, respectively, the restrainers through which part of all the seismic action may be transmitted. Used in combination with bearings, they may be provided with appropriate slack so as to be activated only in the case when the designed seismic displacement is exceeded. I have also to mention that in the current part 2, we have also reference to bearings, and when we say bearings in the current part 2, we are talking about the fixed bearings, movable bearings, elastomeric bearings, seismic links, the devices, and shock transmission unit. This is the situation that appears in the current tab. Now, in the next generation, in the second generation of Eurocode 8 part 2, we substitute the term seismic isolators with a more general term, which is antiseismic devices. And antiseismic devices is not just a seismic isolator. Antiseismic devices covers essentially 2 kinds of devices, let's say. Devices that use as a seismic isolators, but also devices that use as energy dissipation devices, and also devices that provide both of these terms. So we have in part 1.1 the definition for what is the energy dissipation device. It's disposable energy element of the energy dissipation system that dissipate energy caused by relative motion of each end of the devices. It does not form part of the main structural system. So devices that provide energy dissipation. And the energy dissipation system is a collection of these devices. On the other hand, we have the isolators. Devices possessing the characteristic needed for seismic isolation, namely the ability to support gravity loads. This is, in many cases, what is required, at least for the seismic isolators for non-seismic situation, from the superstructure and the ability to accommodate horizontal displacement. The isolation system is the collection of these devices. And finally, but it's important to note that we have also a definition for what we mean with the term of full isolation. A superstructure on isolation system is fully isolated. I'm focused on this because it's very important in this part of the Eurocode. If in the seismic design situation, it remains with elastic rays. Otherwise, the superstructure is partially isolated. So we have fully isolated bridges and partially isolated bridges. This is a definition that will have to be clear in this part. I recall you that the requirement from the mandate is to improve the connection with the product standards. And when we said the product standards in the for seismic isolation, we have to reference not only to what is common sense that we have the antiseismic devices product standard, but also to the typical structural bearings, which is covered by the product standards EN 1337. I remind you that the structural bearings covered by this product standard EN 1337 this standard is applicable to structural bearings where used on bridges or other structures. The European standard does not cover bearings that transmit moment as a primary function, bearings that resist uplift, bearings for moving bridges, concrete hinges, and seismic devices. I remind you, and I ask you to be very careful, that this European standard does not cover this situation. So the EN 1337 does not cover, in general, the seismic devices. Why? Because we have another product standard, which is in EN 15129, which is the scope is to cover the design of the devices that are provided instruction with the aim of modifying their response to the seismic action. It specifies functional requirements and general design rules for the seismic situation, material characteristics, manufacturers, testing requirements, as well as evaluation of conformity, installation, and maintenance requirements. All these tasks covered by the product standard, not by the design standards. So regarding the testing requirements, the evaluation of conformity, manufacturer installation, maintenance, etc., should be referred to the product standard. The devices that covered by the most common devices covered by this standard is rigid connections, is the displacement-dependent devices, is the velocity-dependent devices, and is typical seismic isolator. We have also, in the current version of Eurocode 8 Part 3, reference to this standard, but it's very limited. Why? Because when the code written in 2004, 2003, 2004, this product standard, it's not appear as a standard. It was a kind of pre-standard. So we have a pre-N of 15129. Now we have this as a standard, so we can follow fully this product standard. Just to give you an idea what are covered by this product standard for antiseismic devices, we can have slider, which can express linear response. If we have guided, it can be linked. Otherwise, we have freely displaced. We have elastomeric bearings with low damping or high damping. So we can have a linear response or non-linear response. We can have lead rubber bearings, which again we can have where we have non-linear response. We can friction pendulum system that depends on friction, so is sensitive to vertical load. This is why Professor Franchin also mentioned in the presentation about why it's critical, the vertical action. For instance, for devices like this, the vertical action is very critical. We have also viscous damper. This is velocity-dependent devices, and of course, non-linear response. Also have spring viscous dampers. Again, we have a non-linear response. But what is more important showing all these devices is that many devices finally provide a combination of isolation from one hand, lengthening the period, this is the aim of the isolation, and energy dissipation, so increasing damping, is the other hand. So we have a combination of this, and we cannot, of course, in any case, consider these two effects as separately, because already it's combined. Now, why I mentioned two product standards instead of one? Because, well, all we know very well that the antiseismic device covered by EN 15129. But also in Eurocode 8 part 1-1, we have a strictly mentioned that in low seismic action class, rigid connection devices and bearings, structural bearings, should conform not to antiseismic devices, but to structural bearing devices. To this standard, to EN 1337. Or if you don't cover by the standard, you can cover by European technical approval, but this is something that has to do with the conformity or to a standard or to a European technical approval process. This is the reason that also in this presentation, I have mentioned this product standard. In the majority of cases where we have moderate or high seismicity, the standard that we have, the product standard that we have follow is the antiseismic devices standard, the EN 15129. Now, going to the main part of Eurocode 8 part 2 regarding the design of bridges equipped by antiseismic devices. With antiseismic devices, I try to point out the additional requirements to EN 1998-1-1 regarding the design of the structure. And starting from what is provided now as a requirement in the part 1-1 of Eurocode 8. You can see that in this, in section 6.8, it covers the design of structure, not bridges, because this is a general part, of structure equipped with antiseismic devices. Therefore, if someone has to design a bridge with a antiseismic device, should be conform all the requirements provided in this section. The only additional requirement we'll find in part 2. And I note this because it's very important that the majority of the requirements for the antiseismic devices, it's covered in part 1 and not in part 2, because it's common for all the structural equipped with antiseismic devices. Regarding now the part 2, if you follow the text of the second generation, you can see that we have eliminate the number of pages to, as I said you in the beginning of this presentation, to no more than 4. Why? Because the majority of the provision that exist in the current part 2 related either to product standard, so we have to remove it because the product standard is not covered by a design standard, but the requirements for product standard covers by the product standard itself. And this is the reason that, as you can see in this slide, the majority of the text already moved because it's covered by a product standard. It's not the correct position here. And also, the common principle that we have for antiseismic devices move also to part 1. And so, we have eliminate more than 30, I think, pages that exist in the current part 2 to 4 pages now in part 2 for the design of bridges equipped with antiseismic devices. You can see, for instance, all the annexes related to the variation of the design properties, to the factors for lambda factors for the common isolator types, the test for the device, for the validation of the device properties. All these tasks are covered by the product standard. And this is why we don't have now in the Eurocode. You cannot find it in any part of the Eurocode. You can find it in the product standard. Now, regarding the seismic action, the basic requirements and the compliance criteria, I have to mention that it's in fully isolated bridges, the superstructure should be remained with elastic rates under the capacity design effect. This is a basic requirement, but we have to note that this requirement affects the fully isolated bridges, and this is important. It's not a requirement for partially isolated bridges. Regarding the substructure or fully isolated bridges again, and the secondary structural members of only a secondary structural members, the isolated support, for instance, of partially isolated bridges, again should be designed as non-dissipative range. And the verification for this member should be according to requirements for ductility class 1. Exception on this is for tall heavy piers or pylons with a very specific situation where we can permit or ask, not permit, ask for design according to the ductility class 2 and not for ductility class 1. So we ask for additional energy dissipation in these members, but this is a very specific case. How calculate the effect, the action effect in the elastic range, that is the requirement for the deck. It can be calculated using the Q factor method, where Q is equal to QS. Another requirement for for bridges equipped with antiseismic devices is that is not the uplift of the seismic isolator permitted, and in case that we have an uplift, should be handled by choosing suitable isolators or restrained to prevent uplift. Regarding the vertical stiffness of the isolators, is a special provision is required according to the part 1-1. We have also for fully isolated bridges a special provision where this condition may be considered to be satisfied if vertical deformation of the seismic isolator are less than 5% of the horizontal deformation in the seismic design situation. This condition may be neglected, of course, if sliding or elastomeric bearings are used as seismic isolator. And another requirement that appears in part 1.1, but it's very critical also and related to the antiseismic devices, is the resetting capability that required to have the isolator and the isolation system. According to part 1.1, we have the reversible stored energy, which is the sum of elastic strain energy and potential energy, should be greater than 1/4 of the energy dissipated by the devices. If we satisfy this equation, we have this principle, we have satisfied the resetting capability requirement. But this is it recognizes that this is in practice, it's not very common very trivial to calculate. Therefore, we provide, and this is something that appears in the second generation of the Eurocode, we provide an alternative requirement for a system with a bilinear behavior, where we ask to satisfy a specific relation regarding the displacement. And also, even you cannot satisfy this equation, which is, I don't want to go in details for this, you have also the ability to cover the requirement by increasing, as code already defined, the design displacement for the isolator by a factor of rho d, which is also provided by the code. So for the rescheduling capability, which is in some devices like the friction pendulum system, it's critical. We have the main principle, the principle that should be satisfied, which is the base is based on basic principle of mechanics. We have an alternative, which is a simplification. And if you cannot satisfy the simplification, we have a more simplified approach, which is just increase the displacement by a factor. Regarding the method of analysis, I don't want to go in more detail. We have all the methods that is appear also in general part and also in part for bridges. We have the lateral force methods can be applied, the equivalent in the response spectrum and response history. What is important that in fully isolated bridges, the effect of vertical component of the seismic action may be determined by equivalent linear response spectrum analysis, regardless of the method used for the determination of the response in the horizontal direction. So for the vertical, we can have a response spectrum analysis, and for horizontal, we can have other methods of analysis. Typical methods for the analysis of bridges equipped with antiseismic devices is the equivalent lateral force method, a single degree of freedom system method where all the bridge is model as a single degree of freedom system. The code provide the properties of this system, and with iterative method, you can end up with the requirement for the design displacement of the isolators. And for the isolators. The second method is based on a linear response spectrum method, where essentially we modify the design spectrum by the introduction of a damping modification of the damping in a special range of the spectrum. And of course, as in any case, we have the ability to perform a response history analysis for take into consideration the full response for the antiseismic devices. A closing, we have the minimum overlap length, which is also Mr. David already mentioned. Yes, regarding the overlap length, we have a requirement that a minimum overlap length will have to be satisfied at the supports, where relative displacement between supported and supporting members is intended under seismic design condition. A minimum overlap length should be provided, and the code provides this minimum overlap length, which should be such as to ensure that the function of the support is maintained under the total design displacement in the seismic design situation. And you can see that we have this overlap length. It's divided in three parts. The first part related to the minimum in any case overlap length. The second is related to the spatial variation, or as Professor Sextos already mentioned. And the third term is, of course, related to the design displacement, seismic design displacement. Now, regarding, because I also see a question regarding the joints between two bridges or separation joint between the two bridges or two sections of the deck. I remind you that the Eurocode 8 Part 2 provide the solution, ask for use the SRSS, the square root of sums of square, for the two separate the individual overlap length to be applied for the separation joint. And this is my last slide, but I want also take this opportunity to thank you for your attention and to also say that the design of bridges with antiseismic devices is not only for the design of new bridges, but it's also a method, and you cannot also use as a design for the intervention of upgrading of existing bridges. So we have a method here that is also provided for new structure, but this method and this principle and all the requirements also applied for the existing structure. This is covered by Part 3 of Eurocode 8 as a method of intervention. Thank you very much.
Thank you also, Mr. Panagiotakos, for your presentation. We would have time for one or two short questions. No question arrived as per chat. If not, allow me to address one short question. Namely, for buildings equipped with antiseismic devices, we actually always have a limitation regarding the application of simplified design methods. Namely, we should refer to a eigenperiod, a maximum of 3 seconds. Is there a similar regulation also for bridges?
No. And I want to point out also this, let's say, a big difference between building and bridges. Bridges, compared to buildings, are very simple structure. They can be simulated as a single degree of freedom system, the isolated bridges, seismic isolated bridges. And all the mass is concentrated essentially in 1 degree. And we don't have any participation of a dynamic response of the deck. And essentially, even in the transverse direction, the deck is essentially rigid if we have an isolated structure. In the contrary, in buildings, it's not this situation. In buildings, even in the isolated building, we have a contribution for the dynamic characteristic of the building itself, of the superstructure. And this is the reason that we don't have limitation, such kinds of limitation for bridges.
Thank you very much once again. We have received, meanwhile, a question by chat. Just one moment. Is the equivalent single degree of freedom method applicable for long continuous span bridge with lead rubber bearings from Sudip Shrecha? Is the question.
Yes, thank you. The part 1-1 provide the limitation of this method for a single degree of freedom system. And if I remember correct, there are no limitations regarding the length of the bridge. There are other limitations related, for instance, if we have special cases, but if I remember correct, and please correct me from the colleagues, there are no such limitation for long span bridges.
Thank you. And one more question from Michael. Are those dampers used in vehicle bridges similar or different than those used in pedestrian bridges? The dampers used in pedestrian bridges that absorb vibration of pedestrians, like the ones used in Millennium Bridge?
Yes, we are talking about essentially shock transmission units than the dampers that we have to dissipate energy. But I can compare these dampers that, for instance, for the Millennium Bridges, similar dampers are used in some cases in the railway bridges, because railway bridges who have in longitudinal direction, who have railway seismic isolated bridges, who have also to accommodate the traction of the train, so we have to provide with a shock transmission units mainly in the horizontal direction and also in the transverse direction in curved bridges. The dampers, this kind of damper is not related to the seismic isolations as energy dissipation devices. It's for other reasons. It's to reduce either the dynamic effect or to accommodate the traction and acceleration forces.
And one last question from Stefano Barone from Franchin. Is there any change regarding required performances about the use of elastomeric bearings and rubber isolators? Sometimes design is made with normal elastomeric bearings with a function of isolation, but no performances checks would be required in this case. Type tests or FPC tests and so on.
Yes. This is something that we have solved, in my opinion, in the next generation of the Eurocode. We refer to a product standard. So all the requirements described in the product standard and the design of the isolators are also mentioned during my presentation. Also, the test, the installation, the maintenance, everything described in the product standard. So when we said that we have an isolator, let's say an elastomeric bearing, according to a specific product standard, the elastomeric bearing should be designed to fulfill the requirement of this product standard. So we don't have in Eurocode to mess if you have bearings, elastomeric, the properties, etc. Everything defined in the product standard, and the designer of the bridge provides only the required properties for the isolators only.
Thank you very much once again. I'll pass over to the next speaker and to my colleague, Professor Wiedenweg.